Hey guys, Jason here. Welcome back to the channel. Today we are finally covering the cathode resistor as it relates to a triode gain stage. So many months ago I did a video on the plate resistor and how different values of the plate resistor affects the gain that you get from a gain stage in your preamp. Well, today we're looking at the cathode resistor, right? And what I'm using here is my Dirty Shirley clone. It's a JCM 800 preamp, basically, right? And it's got a three-way structure switch, which sets three different cathode resistors on the second gain stage. So we're going to use this amp as the test case for today's video, right? I'm going to take a bunch of measurements from the amp in the three different settings, and we will get straight into looking at load lines and a bit of theory and trying to understand why these different cathode resistors actually give you not only a different level of gain, but a different sound, different tonality, right? So let's get into it.
We're going to start this segment by having a look at our trusty triode gain stage, right? So as we would see in 1/2 of a 12AX7. Now the diagrams that I'm using in this video have been lifted from Valve Wizard, the website. So Merlin, if you want to understand in great depth about all kinds of things related to tube amps, particularly as they relate to guitar, please check out the website. Full credit to Merlin, and I highly recommend this book, right, which is absolute Bible with respect to these topics, right? So I'm definitely lifting knowledge that I've gained from this website and also from the book and lots of other sources, and I'll just try and explain these things in a hopefully an understandable way. So we should all know that in a power stage you have to bias. In a fixed bias amp, you have to adjust the bias of the power stage, an EL34 or 6L6, what have you. And a triode, 12AX7, or a preamp gain stage, is actually no different, right? It is a gain stage. It needs to be biased to give you, optimum amplification. And you can adjust the bias of it to get different characteristics in that amplification. So what we're seeing on screen here is akin to what you'd see in a fixed bias power amp tube, right, where you would have the cathode tied directly to ground. You'd have a negative voltage on your grid, right? So fixed bias meaning adjustable bias, right? You would dial this in with a negative voltage, right? So the grid is negative DC voltage compared to the cathode. And then obviously a plate voltage, right? So knowing that, which I'm sure you're familiar with respect to the power stage of your amp, think about that in terms of this preamp tube. Now, you never see this implemented like this in a guitar amp, although you could, right? You could have 12AX7 just like this, tie the cathode directly to ground, but if you did that, you'd need to have a negative DC voltage available to put on your grid, right? So that you could bias the stage of the tube correctly. In practice, it's not practical, right? So what do? Well, we set it up in cathode bias, just like you do, or just like you can, in the power stage of your amp. So rather than applying a negative DC voltage to the grid here, like you would in a fixed bias power stage, the way that it's done in preamp tubes is to cathode bias them. All right, you heard of a cathode bias, power amp? Well, all of your preamp tubes are cathode bias as well. And by inserting a resistor here between the cathode and the ground, when there's current flowing at idle through this triode, you'll develop a voltage across this resistor. And by doing that, you'll end up with a voltage here, right? Let's call it 2 volts. You'll see when I get into the readings, you'll see what the numbers are, right? But let's call this 2 volts. Right, if this is 2 volts and the grid DC is 0, right, and your preamp, it'll be 0, then effectively the difference between this voltage here being positive 2 volts and this voltage here being 0 is -2, right? So it's the relative voltage that matters, not actually the voltage to ground that matters, it's the relative voltage that matters. So by putting the cathode resistor there, what we're actually doing is creating a negative bias voltage that the grid sees as relative to the voltage on the cathode. Okay, it's easy. You set it up, you bias your tube, no worries, right? And what you can do, and what we're going to explore in further detail, is what happens when you choose different values, right, of this cathode resistor, because not only will you change the gain that this gain stage is capable of producing, but you'll change the characteristics of the gain as well with respect to harmonic distortion and so on. So let's get straight into talking about the amp that I'm using to do this test, right? I'm using my Dirty Shirley clone, which is the preamp of a JCM 800. Okay, so I'm using this fantastic schematic which has been on the internet for a long time. Mark Huss, I believe, drew this up. And what we're doing is we're going to use 3 values here on this second gain stage cathode resistor. Okay, so you've seen me go through this before. Your guitar amp your guitar signal comes in here. This is the first gain stage, right? And the JCM 800 2204. Your signal passes through this coupling cap, through the low jack, into the second gain stage, right? So it's the second gain stage that we are evaluating here. We're going to try 3 different values in here. It's the structure switch, right? So if you know the Friedman amps, you know, Bogner has this kind of concept as well, as does many others. You can switch different resistor values into this cathode to give different, you know, tonal characteristics and feel to the amp, right? Changing the nature of this gain stage completely. Right, so knowing the gain stage that we're dealing with, here I have just marked up in this table the voltage readings from the second gain stage, right? So I've got a 3-way structure switch in this amp, and in the lowest gain structure, it's a 10K cathode. This is your classic Marshall JCM 800 2203 2204 cold clipper. Okay. In the middle position, we switch in an extra resistor which has a combined resistance with the 10K to be 3.2K, and then finally the highest gain position on the switch is 2.5K and has a bypass cap, a 0.68 microfarad bypass cap, and we'll talk about what bypass caps do on a cathode resistor in a triode gain stage a little bit later. All right, but here are my voltages. So this is the supply node to the preamp, 265 with the 10K, right, plate voltage on that second gain stage, and the measured voltage on the cathode. And you can see as I reduce the value of the cathode resistor, the node voltage actually drops, right, because we're getting more current flow coming through the triode, so it's drawing a bit more current, we're getting a bit more load, and that's coming down, and you can see quite a big impact on the plate voltages here, right, when you set up these different cathode resistors. So we will get different tonal characteristics as well as a different amount of gain from these 3 setups, and we're going to explore that by looking at load lines. So to explain what is going on with respect to these 3 different cathode values, we're going to have a look at the dreaded load lines. Now, if you're new to load lines or you're looking for a bit of a kind of refresher, I do recommend having a look at the video I posted a few months back now on drawing load lines for different plate value resistors, right? And this will tell you, or that video will explain kind of how I drew these, but these are the three load lines that we've got for our second gain stage here. It's got a 100k plate resistor, right, or anode resistor, and then we've got the 10k, 3.2 and 2.5. The only reason that these are slightly apart is because when we saw the voltages on the previous, on the slide that I just had up, the voltages are dropping a touch as the node voltage is dropping as I started to decrease the value of this cathode resistor. Okay, but simply put, the way you draw these is you figure out the point here, which is basically the node voltage, right? Which is 265 volts at this point, 0. And then to get the other point, which is at the point where the plate voltage is 0, you've got to imagine that triode stage, or that gain, gain stage being short-circuited. So you can imagine the high voltage supply through the plate resistor short-circuited to ground. What's the current that's going to be flowing through that plate resistor? You've got 265 volts to drop, so you can work out the milliamps, right? And that gives you that point on the graph, and then you can draw your line. The point of this line with respect to the cathode resistor is it shows, let's just focus on the blue line, right? It shows all of the possible operating points or bias points for this gain stage that are available to be kind of dialed in, right? And the way you dial them in is by the value of the cathode resistor that you choose. So it's kind of somewhere here in the middle is, let's call it the golden point, or the Goldilocks point, if you like, right in the middle. As you move down an operating point or a bias point on the load line towards this side, you are going cold bias, and if you move from this midpoint towards this side, you're going warm bias. So let's go straight in and draw our cathode lines on here, right? So here's the load lines we had before, right, for the plate characteristics of the triode gain stage, a 12AX7, and here are the cathode lines which come as a result of the blue is the 10K cathode, right? The 3.2 is the orange, and the red is 2.5. Now, let me try and explain how we actually come up with these. So these grid lines here, you see the 0, minus 0.5, minus 1, and so on. This is the grid voltage. This represents the grid voltage. Okay, so remember the triode, we've got the plate, we've got the cathode, the grid voltage coming in. Now we have to bias the grid voltage with respect to the cathode, and as I said earlier in the clip, if our cathode voltage was 2 volts, then the grid voltage is effectively minus 2 as relative to the cathode. So this tells you that on this line here, where this line intersects with the load line is your bias point if your cathode voltage was at 2 volts, right? And now that's important because you can see these grid lines at this end of the chart, they're very flat, right? And as we move up, they get steeper and steeper and steeper. And what that results in is a different voltage swing or amount of gain that you get, right? So the further you are to this side of the chart, the right hand side, the less gain you will get because these lines are flatter. The more you're on the left hand side, the more gain you will get. But you get different characteristics in the gain, and we'll talk about that next. So before we talk about the characteristics of the gain, let's just touch on how we draw these cathode lines, right? So the way to do it is pretty simple, right? So you've got to think of Ohm's law again, Right, so if V equals IR, then you can rearrange that equation to I equals V over R, or current equals voltage over resistance. And let's think of it this way. The voltage on the grid at the cathode is 2 volts, right? And if we have a 10K cathode, you can use Ohm's law to figure out that there is 0.2 of a milliamp that's at idle is flowing through that 10K resistor, right? So you can mark a point on the graph at that point, right? So the 2 volt grid line at 0.2 milliamps, which is here on our graph, you mark it there. You do the same thing at another graph point, right? So do it at 1, you'll get 1 milliamp. You can now draw your line. It's never going to be a perfectly straight linear line because these grid lines, as you can see, are not straight. But, you know, it's close enough for rock and roll, right? I'm just in straight lines in this graph. Do the same thing. 3.2, right? So do the same thing. At 2 volts, I equals V over R, the voltage is 2, the resistance is 3.2K, you can derive the current flowing through that cathode resistor. Do it at another point and then you can draw your load line. And you can see, right, as our cathode goes from 10 to 2.5, we're moving up in terms of the bias point. So at the 10K, our bias point or operating point for the triode is way over here on the right hand side, very, very close to cutoff. Right? So at this point the valve just cuts off and clips, right? That's where you get the square wave. Here we're getting closer to the midpoint, here we're getting even closer to the midpoint. So very, very coldly biased here, and then as we head up the graph we're getting warmer and warmer. So let's just drill into looking at the situation with the 10K cathode, right? So this is the, by ear, it's clearly the lowest gain in the amp, right? But it has a special characteristic about it. It's the cold clipper, and let's talk about why. So as we saw in that last load line graph, the operating point, which I've now highlighted here in green, right? So this is the intersection between the plate load line and that cathode line that we figured out. It's right at this point here, and you can see that it's way, way, way over to the right. So the operating range for this triode stage, it doesn't have a lot of bandwidth here, right? If it's over here in the middle, it can swing back and forward. So what actually happens, right? Well, when you apply your guitar signal to the grid, right, of the gain stage, the grid being the input, you're oscillating that grid voltage, right? So you can imagine if your tube is biased at minus 1.5 volts and your operating point is here, then as your grid oscillates back and forward with the AC voltage, back and forward, then the voltage swing that you get from this gain stage, let's say it goes plus or minus 0.5 of a volt, right? So from minus 1.5 to 1, minus 1.5 to minus 2, that's your grid input. Then the gain you're going to get out of this gain stage is actually going from here, which is, 140 volts, give or take, through to this point here. This is over 205, and that's the voltage swing, or the gain, right, that you're getting from this gain stage. And it's pretty symmetrical because you're in the kind of the midpoint here in terms of operating point. You're getting kind of symmetrical amplification depending on whether, if the grid goes positive or negative. It's pretty even in terms of the output. And you got a lot of headroom here. You got a long way to move before you're going to get this thing into kind of cut off either way. When you cold bias this thing with a 10K cathode, you're pushing the operating point or the bias point at idle way over here. This thing's got hardly any room to move. It's got a lot of room to move on this side, but not much here, right? So it doesn't take much to push this thing into cutoff, but only on one side, right? So whilst, think about our scenario here of 1 volt peak to peak input on the grid. Here's our midpoint. So we're going to go, half a volt this way, half a volt that way. Then the voltage swing we're getting from this 10K cathode is 255 volts to 210. You can mark it out on the graph, right? In other words, a voltage swing of 45 volts. In other words, 1 volt in, 45 volts out. So the gain, that's the gain, right? The gain is 45 volts. So we're definitely getting gain here. It's not as much as you get if your operating point's down this end here, and I'll show you why. But with the 10K, as I just said, right, it takes next to nothing to push this side of the waveform into cutoff. And when you go into cutoff, what you get is a square wave. We'll show this on the oscilloscope. So here we've moved to the load lines for the 3.2K cathode, right? So this is the mid of the 3 gain stages. And this will illustrate how different the gain is compared to that 10K that we were just looking at. And so here's our cathode line. We drew it the same way as I described before. Here's the load line for the plate. And so right here at the intersection is our operating point or the bias point of the tube, and you can see the green lines here, right? This is kind of basically back down to 200 volts. So a minus 0.5 this way on the grid voltage and plus 0.5 this way on the grid, right? So a 1 volt voltage swing from peak to peak. This is what it's going to generate us in terms of voltage swing with respect to the amplification, right? So it's drawing this out, it's 168 to 235. Now that's a voltage difference of 67 volts, right? Compare it to our 10K. Our 10K was 45, right? So this is about another 50% more gain on top of the 10K. It's simply put, right? The more we push this over to the left here, the more gain we're going to get. But it's a different kind of gain in terms of it's way more symmetrical, right? So as I mentioned, right, when the 10K operating point's way over here, we're going to get that asymmetric clipping very easily. This side's going to be more symmetrical. So when we get more gain, it's going to push through the amp with more gain, but it's going to be more symmetrical. So it's going to sound a bit different. So now we're going to talk about cathode bypass caps, right? And I'm going to use another diagram off the Valve Wizards website, thanks to Merlin. This is our bypass cap here. So what is this all about and why do you have it? Well, look, think of it this way, right? If you don't have that in place, we've just got our cathode resistor here, okay? What does Ohm's law tell us? Ohm's law is V equals IR, or current times resistance. So resistance here is constant, but the current is increasing, right? So as we get more and more gain out of this thing, think of this in an AC perspective, right? More and more gain out of this gain stage, more and more current. That means the voltage here at the cathode is actually going to go up. All right, it's not actually going to sit there at the bias point at idle. It's actually going to move up as we draw more current through this thing. And what that means is that our the grid bias point, right, as relative to the cathode is going to change. And what it actually does, it starts to destroy the amount of gain that you get. The more current you get flowing through this network, bizarrely, the less gain you're going to get. So it starts to kind of taper off. And you start to lose the full potential, right, of this gain stage. Now, the bypass cap does, and this is the beauty of DC and AC current working simultaneously on the same wire, is that the resistor sets the DC bias point, just like what we talked about, right? Just like it does in a fixed bias, power tube, just like I've talked about with respect to preamp tubes as well, right? So cathode bias, you can set this 10K, 2.5K, whatever, right? You're going to set your bias point at idle. Now, as soon as you get an AC signal coming through, which is what, the audio, your guitar signal is, as depicted by this little blue sine wave here, well, the AC is actually going to bypass through this guy. Think of it that way, right? It's a bit like a bright cap. It's probably the easiest way to think of it. It actually charges this capacitor, and then this capacitor can release through. And it's just like a bright cap sitting on your gain pot, where frequencies can basically bypass this resistor and just get straight through, right, the cathode up to plate and then out and amplification. So by doing this, it completely negates the impact of the cathode with respect to the amount of gain that you're going to get. You still get the same characteristics with respect to operating point, which I've talked about, but you get significantly more gain out of it. So, I mean, if you've ever tried this, right, you get a 10K cold clipper on a Marshall, put a bypass cap on it, and oh my God, what a difference there is in the amount of gain. And you choose the value of this capacitor. It's a way of tuning the amp, right? A way of tuning the preamp, because the higher this capacitor, the more low end frequencies will be bypassed. And you can see this graph here on the right, which is the amount of gain against frequency, that the higher the value of this bypass cap here, the more of the low frequencies are allowed through, and you just get max gain, right? And smaller, or the lower value that you make this bypass cap here, you get a tapering off, right? So, a very classic Marshall value is 680 nanofarad, or 0.68 microfarad, right? So you can imagine that it's kind of in here. Just imagine it between 1 and 470. Look at the tapering off, right? It's a high pass filter, and it's basically pulling frequencies down at this point here. Right, it's about 200K. So by choosing the value of that bypass cap, you have a huge amount of variation that you can put into tuning and getting and cutting out bass frequencies in your preamp.
So here we are at the bench. I've got the oscilloscope set after the coupling cap on the second gain stage in this DS40, and I've got the structure switch set in the middle of the gain stage scenarios, right? So it's 3.2K cathode, and you can see here, right, that I'm getting a nice symmetrical sine wave. This is after the second gain stage. So the gain, the moment on the gain pot's pretty low, right? It's dialed right down. Now, what we want to demonstrate here is how the three different cathode structures give you not only a different gain amount, but a different characteristic of the gain, particularly the 10K, right? The 10K cold clipper is really what I want to demonstrate here. So we're in the middle position because that's, biased in what I would call the kind of, the middle zone, the sweet spot, if you like. And if I increase the gain here, I'll just bring the scope back to 50 volts per grid. As I bring this gain up, you can see the clipping on either side of that wave, I know it's not perfectly symmetrical, but you can see it's clipping on both sides. All right, bring the gain back down again, bring it back up. You can see it's clipping on both sides. If I go into the highest gain mode, right, you can see that if I bring the gain up, it squares off even more. Bringing the gain back down again, obviously, all the way down, we get a nice symmetrical wave again. Bring it up. So what we're seeing is clipping in that stage that is, largely symmetrical on both sides. Now let me bring this into the 10K cold clipper, which is the middle position. All right, and I bring the gain back up again here. And look what's happening. If I change the scope, zoom it in, you can really see, right? This is asymmetrical clipping. It's only clipping on one side. This is what we're seeing as the waveform, as the grid is pushed one way, it runs out of runway and the valve goes into cutoff and we get the clipping. And when it comes back out, back the other way, and the voltage swings back, negative on the output, the wave continues uninterrupted, no clipping. Right? This is the 10K cold clipper. That's what gives us that asymmetric distortion, which is pretty pleasing to the ear, I think. Right. So let me go back into middle position again. All right. So here we are, and you can see, right, clipping on both sides. So the 10K cold clipper, whilst it's a pretty low gain stage, right? It is the lowest of all the gain stages that we've got in this amp, but it's unique in its waveform.
Okay guys, well, I hope today's video was helpful with respect to understanding the impact of a cathode resistor on a gain stage, and I hope you can find this information useful and apply it to maybe a DIY build or perhaps a mod that you're contemplating to your existing stock amp. If you haven't subscribed to the channel yet, please do. Ring the bell, you'll be notified of new content, and I'll catch you later.